start in chapter 5. In chapter 5, it's all about free body diagrams and forces and trying to understand what's going on. So this is the way the class is set up. We spent the first 4 chapters figuring out about motion. We talked about motion first in a line, then we talked two-dimensional motion, we talked about circular motion, we talked about projectile motion. We talked about vectors and how vectors add graphically, and then how you take vector components. That sets us all up so we can handle forces. Why do we care about forces? Well, this goes back to Newton, Sir Isaac Newton. Because Newton realized that, yeah, objects accelerate, their velocity changes, but where's that acceleration come from? That acceleration comes from a force. And it takes a force to create an acceleration. And there are many, many different types of forces. All right, so let's look at some of the different types of forces that exist out there. So, usually, since before we had online classes, I would ask the students, I said, name some kinds of forces that exist. And then what kinds of forces they are, and let's talk about them and how they react differently. So you can have forces like you can have gravity. We've already been talking about gravity as an acceleration, but really gravity is a force which produces the acceleration. We have forces like spring force. If you have a spring, it can apply a force. We have tension, which is if you have a rope or cable tied to something, you can pull on it. We have just simple things like what we call an applied force. Applied force means I just push on the wall, my hand is creating a force on that wall, or I push on this eraser. I'm applying a force to that eraser. So we call that just an applied force, or we're going to drop that when we put it into a problem, we're going to just call it a force. We also have forces of friction, which is a force that opposes the motion. In friction, we usually talk about friction between two objects. So if I'm sliding my hand on this this whiteboard here, I feel a friction. I feel an opposing force to my motion. You can also have friction in the air, which we usually call drag, which is the friction of the air acting on the object as it moves through the air, also known as air friction. We can have thrust, which is what comes from like a jet engine, or even a propeller in an airplane, produces thrust. It actually pushes the air backwards, which pulls the airplane through the air, or forces it through the air through Newton's third law. So thrust is another force. All right, we also have like a magnetic force, or we'll call it magnetism. If you get two magnets close to each other and they're to have the same pole, north and north, they're going to repel each other. If you have north and south, they're going to attract each other. So there's the magnetic force between the two objects. So all these are forces. We can also have something called a normal force. And if you took a physics class in high school, I'm sure you know all about a normal force. We'll talk about that in more detail because that's a critical force. So these are all forces. Now, there are 2 special forces on here. This one, magnetism, and gravity. Not all the ones in between, just these 2 special forces here. I should draw it like this because that looks like they're all in play. These are forces that work whether you're contacting or not. So all the rest are what we call contact forces. These are what we call non-contact forces. Meaning gravity works just as well when you're not touching anything. If you're just floating around, you still feel gravity in space. Magnetic force too, you don't actually have to touch the magnet to the object to feel the force before you even get to contact. All the rest of these, there must be contact between the objects. For the spring has to be touching the object. The tension, the rope has to be connected to the block or whatever you're trying to apply the force, or there's no tension. Applied force, you have to have contact to make that force occur. Friction, the same thing. There has to be contact between the 2 surfaces or there's no friction. Drag, yeah, you have to be in the air, or contacting the fluid. You could do it as any kind of liquid if you're trying to go through water. There's a drag force, so you're touching that object. Thrust, same thing. An airplane propeller does not work in space because you can't move the air through it if there's no air. And a normal force is a contact force between an object and whatever surface you're touching, like the ground or a desk or something like that. So the only ones here that are non-contact forces are gravity and magnetism. All the rest of these are what we call contact forces. And so there must be contact for those forces to occur. All right, let's talk about friction, because friction is a special force here. We're going to deal with friction more later, but friction actually has two different types of frictional force. You have the frictional force that opposes an object from moving. So when I try to push this eraser, it doesn't move at first, even though I'm pushing it. I'm not pushing it very hard, but I'm pushing a little bit. And then all of a sudden it starts to move, and then it slides pretty easy. As if you ever tried to move like a heavy couch or refrigerator or something like that. The hardest part is getting it moving. And once you get it moving, you're like, oh, keep it going, because you don't want to stop again and have to overcome that. So we have the motion, or we have friction when it's not moving. We call that static friction. And then once it starts to moving, that switches to kinetic friction. Or this is the friction of motion. Now there's also a friction if you have a wheel or a ball. We call it rolling friction. Okay? Because rolling is a whole different motion, which we will talk about when we get up to chapter 12 or so. So it's a ways down the road, but we'll talk about rolling motion. Right now, rolling motion, most of the time we consider this as a very small effect. Meaning if you put a ball on a table, it will move very easily. So the rolling friction is very small. But there is a friction there because the ball won't roll forever. It will stop because of rolling friction. Most of what we're going to deal with in chapter 5, 6, 7, and 8 is kinetic and static friction. Now remember, if it's not moving, it's static friction. Kinetic friction is when it's moving. Just remember that. In fact, kinetic means motion, so that's an easy way to remember. So those are our different types of forces. What we're going to talk about in this chapter is something called free body diagrams. Free body diagrams are how we're going to analyze problems dealing with forces. And you must do free body diagrams. And when you do your problems, if you don't have a free body diagram, you're automatically going to lose like 40%. Even if you did the problem right. If you don't have a free body diagram, you're just going to lose it. So you just got to get used to doing free body diagrams. No matter how simple it is, just do a free body diagram. So let's do a case where we have a free body diagram. I'll show you what I mean by a free body diagram. Sometimes called a force body diagram, but I'm used to the old school notion. It's called a free body diagram. So let me grab my tennis ball on a string here. Here's the tennis ball on a string. So I'm just holding it here. Okay? So this is the situation. Tennis ball on a string. The tennis ball feels gravity. Everything feels gravity. So there will always be gravity. But then there's string tension that's keeping it from moving. So it's just hanging there. So here's my tennis ball on a string. So my free body diagram is always going to be some point off to the side. I'm always going to draw a dot for the object. Technically, that's the center of mass of the object. Okay? And we'll talk about center of mass when we get up to chapter 12. So that's the center of mass of the object, and we want all forces to act on that center of mass. When we get to chapter 12, we don't. But right now, we're going to just worry about that. So what you always have is gravity. What I want you to do is, gravity is always going to be down. So just make gravity down because it conceptually makes a lot more sense. I've seen people try to rotate it and stuff like that, and it just gets confusing. It's not intuitive. And then I don't want you to write force of gravity. The force of gravity, we're going to write as m times little g. Force of gravity. Because gravity is equal to your mass times the acceleration of gravity, which I already talked about. Little g is just the constant. It's 9.81 meters per second squared on the surface of the Earth. Okay? And times your mass gives you gravity. So we're going to write this as just mg. So this is the mass of the tennis ball. So the tennis ball has a certain mass. Remember, our fundamental unit of mass is a kilogram. So this is going to be in kilograms. Okay? And then we have another force acting on it. Let me change colors here. We have a force from the string. But the force from the string, we're going to call tension T. And notice those have to be the same length of arrows, because the force is a vector. Sorry, force is a vector. Okay? And so those have to be equal because the tennis ball is not moving. They have to balance each other out. So in this case, the force of gravity balances the force of the tennis ball. Or the tension in the string, I'm sorry, balances the force of gravity. Okay, so I want your free body diagram to reflect that too. Make those balanced. Okay, make the arrows exactly the same length if it's not moving in that direction. If it's accelerating downward, then tension would have to be less. If it's accelerating upward, tension would have to be greater than this. So if you do the free body diagram right, it's really easy to figure out the rest of it. Now on this is a very simple example because the tennis ball is moving. And it's only got two forces. Some of them can have many, many forces and it gets more complicated, which we'll do in an example. But before we do that, I wanted to talk about the units. We'll talk about this shortly, but you've probably already heard it, that Newton's second law is that the force is equal to mass times acceleration.